So yeah, I'm going to talk about quantum worst case to average case reductions for all linear problems, and this is based on joint work with Sasha, Tom, Igor, and Satya. So the problem that we are considering in this work is that suppose I have a problem P that I want to solve, but then I don't really care about succeeding on all possible inputs that I can get for P, but I want to come up with a solution that that like succeeds on maybe like 50% or 10% of possible inputs. And then I want to compare like hardness of coming up with such a solution versus a solution that is correct on all possible inputs. And this is called the study of like average case complexity. And basically we want to compare how hard it is to come up with a worst case solution versus an average case solution for different problems. So one of the like most powerful tools in the average case complexity are worst case to average case reductions, and whoops. And the goal in this type of reduction is that you assume that you are given worst case input, and you want to somehow like decompose that worst case input into like a bunch of random instances for the problem, and show that you can use the average case algorithm to use on the average to use on like random inputs and then merge them together to get a solution for the worst case input. And there are like two general perspectives about this kind of reduction. So if you are an optimist person, you probably like look positive about this, and you think that okay, maybe it's easier to find a solution that's not always correct, and then I can use the reduction to get a solution that's correct on all possible inputs. But if you are a pessimist person, like like oftentimes in cryptography, people like assume that the problem is like very hard to solve because it's even hard to solve on average. And well, in this work we propose a framework for proving worst case to average case reductions in the quantum settings using some techniques from additive combinatorics. And in particular, we use this framework to prove such reductions for all linear problems, and also we got average case query lower ones for the matrix vector multiplication problem. So let's like briefly review what do we mean by linear problems. So like linear problems is like a set of very fundamental problems, and includes problems like polynomial evaluation, discrete Fourier transform, and many problems in coding theory. And it's defined by collection of matrices M, and the input is a vector V in a finite field to the n, and we want to compute the product M times V. Okay, but in this presentation, I'm going to focus on reduction for matrix vector multiplication problem, and the setting that we are considering here is that we have a like unitary algorithm that has query access to a matrix M, and it gets a vector V as input and output something that's correct with probability 1%. I mean, it equals M times V with probability 1%. So let's have a high-level overview of how this reduction works. So first, this is the main theorem that I'm going to discuss in this presentation. Suppose you have a quantum algorithm that gets a vector V in a finite field, and it makes Q like queries to the oracle for matrix M, and it outputs the correct answer with probability alpha. And note that here the probability is over the choices of V and the randomization of the algorithm. And then we show that there is a quantum algorithm Alex star that gets a vector V, and it essentially makes the same amount of queries plus like an additional term n to the power 1.5. And it has the guarantee that for all possible inputs V, it outputs the correct answer with high probability. And as a corollary, we can get that, I mean, because previous work has shown that matrix vector multiplication has worst case query complexity of n squared, then we can also prove that the average case query complexity of matrix vector multiplication is also n squared. And note that the first algorithm succeeds on 1% of the inputs, but the second one succeeds with higher probability for all possible inputs. Okay, so I'm going to make some simplifying assumptions for this presentation. In particular, I'm going to assume that alpha is a constant. Also, I'm going to set the field to be the binary field. And also, I'm going to make an additional assumption. And this assumption basically says that suppose that the algorithm that we have, the average case algorithm that we have, takes an input v, and if it outputs the correct answer for v, it basically if v is a good input, it outputs the correct answer with high probability over the randomization of the algorithm. So I kind of want to get rid of the random choices of the algorithm. I want to define a set of good inputs versus a set of bad inputs. All right, so for warm up, let's see what we can do when the success probability of the average case algorithm is close to 1. Okay, so if alpha is something like 0.99, then we know that the algorithm succeeds with like such probability, and then we can do linear like self-correction to go from average case to worst case. And what do I mean? This is a very known technique due to Bloom, Luby, and Rubenfeld in I think 80s. It's a very well studied technique in complexity theory, and it's very simple. It basically works as follows. So suppose the worst case algorithm works as follows. Suppose you get v as input, you just sample a random vector u, and then you return the average output of the average case algorithm on u and v minus u. And the correctness like follows from the fact that mv equals mu plus m times v minus u. And the key here is that u like is a uniform random vector in this space, and v minus u is also a uniform random vector in this space. So we can just use union bound to show that this succeeds with high probability, and then we can repeat the same like process many times and take a majority vote to increase the success probability. And the query complexity is amazing because we're just like using the average case algorithm like 2 times. So it's 2 times the query complexity of the average case algorithm. And note that this is like completely classical. I mean, no quantum, nothing quantum is involved here. But the question is, can we do better? So let's say for now that we have like a magical box that is basically a matrix vector multiplication verifier. So what does it do? It gets a v and a b, and it tells us whether mv equals b or not. And it does it in a way that's essentially more efficient than computing m times v and checking whether it equals to b. And we'll see later that we can how to come up with such a verifier. But let's for now assume that it exists. So how does like such a verifier help? So we can use the same BLR technique, but this time we can assume that the success probability is just 1/2 plus some constant epsilon. And this means that if we like do take the sample u and v minus u, then by union bound the success probability will be greater or equal than 2 times epsilon, which is a small constant. But here, because we have verification, we can just repeat and verify to eventually get the correct answer. And we need to like repeat this O of 1 over epsilon many times. So I guess the conclusion that I want to make from this slide is that if your reduction succeeds with some small constant probability, that's also sufficient, assuming that you have efficient verification. Okay, so let's talk about the more interesting low agreement regime. So let's assume that alpha is very small; it's like 1%, and let's see why like BLR doesn't work. Okay, so I'm gonna like design an algorithm that gets an input v, and it computes mv, but for some reason it checks whether I mean, if the first element of V is zero, it outputs the correct answer, but if it's 1, it just outputs some junk. Then in this case, the success probability is like clearly 1/2. But if you get an input that has 1 as its first element, then you have no way to decompose this vector into a bunch of vectors that they all have like 0 as their first elements. Okay? So here's where the additive combinatorics comes into play. So let me just define some basics of additive combinatorics, in particular some sets. For a set X, which is a subset of, in this case, F2 to the n, we can define X plus X to be a set of all elements A plus B, where A and B belong to X. And similarly, we can define 3X, which is X plus X, or Tx, like more general definition. And in general, what additive combinatorics care about is that if you know something about the size of X plus X, or like 3X, what can you say about the structure that exists in the original subset X? Okay, the main technical lemma that we use from additive combinatorics in this type of reduction is Bogolyubov's lemma, which is from many years ago, and it says as follows. Suppose you have a set X, which is a subset of F2 to the n, and the only thing you know about X is that it has some small density. So the size of X is alpha times 2 to the n. And you can think of alpha as being like 1%. And then it says that if you have such a set X, then there exists a subspace V in the subset 4X, and the codimension of V is a function of alpha. It doesn't depend on n. It's like 1 over alpha squared. Okay? And now you might say, okay, this might be nice, but how can we use it? And my response is that, okay, I really don't know how to use it in this form, but what we can use is like a more, it's a nicer description of this lemma, which is the probabilistic version. So again, we have a set X, which is a subset of F2 to the n, and we only know that the size of X, density of X is at least alpha. And then we can say that there exists a subspace V in 4X, and we also have this additional property that for all elements V in the subspace, if you sample 3 random elements from your entire space and let the fourth one be V minus X1, X2, X3, then the probability that all 4 of these elements belong to the X is actually greater than some function of alpha. So this means that each element in the subspace has many representations in this subset 4X. And there's also improved version of this lemma due to Sanders, which is called the quasi-polynomial Bogolyubov's lemma, which improves the dependence of the codimension on alpha. But for this presentation, we don't really need to care about this. Okay, okay, so here's the main question: how to use this lemma to derive a worst case to average case reduction. So here's what we're going to do. So we define set X to be the set of good inputs, the inputs that the average case algorithm outputs the correct answer with high probability on those inputs. And by definition, we know that the average case algorithm succeeds with probability alpha, so the density of set X is at least alpha. And then we want to construct this worst case algorithm as follows. So if the input V is in X, then we are good, because we know that this is a good input, and we can run the average case algorithm, and everything works perfectly. But what if V is not in X? Then we can we can let V be the subspace that we get from the Bogolyubov's lemma. And then if V is inside the subspace, we can sample a representation A1, A2, A3, A4 such that the sum equals V. And we know that with some constant probability, all these 4 elements belong to X. So we can use the average case algorithm to compute the matrix vector product for all of these 4 elements and sum them up. And then we know that this like event happens with some small probability, like alpha to the 5. But remember that we have this like efficient verifier that we can use to amplify the success probability. So we just need, at the end, we just need to do like 1 over alpha to the 5 times. But here's the question: what if V does not belong to the subspace? And I guess like better question to ask here is that what is the subspace V in the first one? I mean, I just told you that such subspace exists, but I didn't like tell you anything about what structure it has. And the way that the subspace defined is that we define this like we let 1x to be the indicator function for the set of good input x, and we let R to be the set of all heavy Fourier coefficients of this indicator function, all the Fourier coefficients that are larger than alpha to the power of like 3/2. And then the subspace is defined as the set of all vectors that are orthogonal to the all elements in R. Okay, so here's I guess the part that like quantum gets involved, because we know that finding the subspace V relies essentially on finding the heavy Fourier coefficients of this indicator function 1x. So the first quantum algorithm that we need to use is to apply like Fourier sampling algorithm to find heavy Fourier coefficients of this indicator function. And remember that we assume that we have an efficient verification algorithm, so we can essentially run the average case algorithm and then verify. And if the answer is like if the output is yes, if the output is 1, then this basically gives us the output for the indicator function on x. And we show that we can use a quantum circuit with a linear number of gates to sample like heavy Fourier coefficients of this function. And the total query cost is amazing. It's poly alpha. It doesn't depend on n, so we can think of it as basically having constant query complexity here. And it has this property. I mean, the circuit has this property that outputs the Fourier coefficients with probability that is like little o of the actual weight of that Fourier coefficient. Okay, and let's return to this efficient verifier that I mentioned. So the rough idea is as follows. So we know that each element of the matrix vector product MV, we can like use n queries to evaluate that particular M. We just need to read one row of the matrix M and multiply it by the vector that we have. And I mean, using this, we can basically construct an oracle for the ith element of the output of the algorithm minus the actual output that we want to see. And this, like each query that we make to this oracle costs like n queries to the original oracle for the matrix M. And the question that we want to answer here is that whether this like functions from n bits to 0, 1 is the all zeros function. I mean, if it's the all zeros function, it basically means that the output of the average case algorithm equals the actual value that we want. But if it has at least one non-zero element, then it means that the output was wrong. And we can do a Grovel-like search to basically detect whether this is all zeros or not, using n to the power like 3/2 many queries to the matrix M. So to put it together, what we are proving is that we are assuming that there exists an algorithm that makes qn queries and succeeds with probability 1%. And we want to show that given that algorithm, we can construct a worst case algorithm that makes O of qn queries plus n to the 3/2, and it succeeds for all all possible inputs with high probability. And the way that the reduction works is as follows. We just define a set X to be the set of good inputs. And we use the first algorithm to sample like heavy Fourier coefficients of this indicator function. And we use these coefficients to find a basis for the subspace V. And using that basis, we can write the input V as a vector V plus a sparse vector S, where this like the amount of non-zero elements in S is a function of alpha, and we assume that alpha is like 1%. So we only need to like read constant many rows of the matrix M to output M times M's. And we use the Bogolyubov like self-correction idea to compute M times V, because we know that V belongs to the subspace now. And we just need to return the sum to get the output for the original input. But so I mean I discussed these ideas, but I was cheating a little bit because I made this assumption that basically the algorithm outputs, I mean, either the correct answer with high probability or the wrong answer with high probability. But we can think of a scenario that the algorithm, I mean, for all inputs, the algorithm decides to output the correct answer with like probability 1%, or with probability 99% just output some junk. Okay, in this case, we cannot like easily define a set of good inputs, because on all inputs we are like having a success probability of 1%. So to overcome this difficulty, we need like a more robust version of this Bogolyubov's lemma, and indeed we prove a robust version that also works for the indicator functions that are like noisy. And let me just mention like a few open problems. So we don't know about a classical worst case to average case reduction for matrix vector product because we have two main barriers. First of all, we don't know how to efficiently verify such a thing classically, and also we don't know how to. I mean, we can sample heavy Fourier coefficients, but it's going to be more costly than computing the matrix vector product like directly. So it kind of doesn't make sense. And also, it will be interesting to see whether we can extend these kind of reductions to not only like linear problems, but maybe quadratic or low degree problems in general. And also, one interesting open problem is to think about the case when we're like encoding an exponentially large vector as like a quantum states of into the basically like considering n qubits and then encoding an exponentially sized vector into the state of those n qubits. For example, like the setting of HHL algorithm. So it would be interesting to see whether we can show such reductions in that case as well. And yeah, thank you.
Okay, time for questions. You have questions?
Hi, thanks for the great talk. What's the cost of the reduction?
So the cost of the reduction has a dependence on. So if we assume that the average case algorithm makes like Q queries, then the cost of the reduction is a function is O of Q plus n to the 3/2, where that O depends. I mean, it's hiding a constant that depends only on alpha, which is the success probability of the average case algorithm.
Okay. Thank you for the talk. So regarding the open question 3, what do you think is a limitation for extending to the exponential cases? So is it the verification procedure achieves only quadratic speedup or something?
Sorry, I didn't.
The reason. So on the open problem 3, third open problem. So what is the intuitive limitation of the current technique? Is it the verification procedure only achieves global type speedups?
So I'm still not sure whether I understood the question correctly, but so what I meant by the open problem 3 is that, I mean, so far in this type of reduction, we're assuming that the input is given to us like as a classical or like as an oracle that we can query classically. But I guess it would be interesting to think about a case where you have like an exponentially large like input vector, and then you want to like compress it into. I mean, you want to compress it into like the into n qubits, such that like when you measure those n qubits in like a different basis, you get like one element from that exponentially large vector. And I guess it would be interesting to know whether we can show such a reduction for that kind of that kind of like that setting of problem as well.
Okay. Yeah, thanks for the talk. I have a pretty technical question. So at the very end, when you decompose V to V prime prime plus S, why is S sparse? And,
it's because the codimension of the subspace V only depends on alpha. It was like 1 over alpha squared. So you can basically diagonalize the basis that you get for V, and you will get like 1 over alpha squared many coordinates that you can change in your original vector to push it into the subspace.
Okay, kind of. Okay.
Okay, one last question.
Hi. Do you think if your additive term can be improved?
Like you mean the n to the power?
Yeah, 1.5.
I'm not sure, but I guess in this particular case, I don't think it will give us like any like a specific improvement, because we already know that the worst case complexity of matrix vector multiplication is n squared. So as long as it's strictly less than n squared, the reduction will go through. So I'm not sure whether like one can get yeah.
Okay, thank you.
Okay, so this concludes the afternoon session. Please join me to thank all speakers in this session.